In this part, we'll be discussing about closed packed structures. In the formation of crystals, the constituent particles in the solids try to pack as closely as possible so as to attain a state of maximum possible density and stability. Since in different crystals, the units of patterns have different shapes and sizes, the actual mode of closest packing is different for different crystals. So in this section, we shall focus on close packing modes of spherical particles of equal sizes. In metallic crystals, the constituent particles are nearly of this type. So let us discuss about the close packed structures. In solids, the constituent particles are close packed, leaving minimum vacant space. The vacant space should be minimum. That is the efficient type of packing. So the first one, close packing in one dimension. We can see here the particles are arranged in one dimension. Each sphere is in direct contact with two other spheres. Spheres of equal size are arranged in horizontal row and they are touching each other. In this arrangement, each sphere is in contact with two of its neighbors. You can see here, each one is in contact with two of its neighbors. The number of nearest neighbors of the particle, that is the number of particles surrounding this one particular particle, is called the coordination number. The number of nearest neighbors of one particle is called the coordination number. In this case, the coordination number is 2. So close packing in one dimension is very easy. The arrangement you can easily understand from the diagram itself. Close packing in two dimension. When the rows are placed adjacent to each other, it results in a two-dimensional close packing. The rows can be combined in two ways to form a crystal plane. First one is called the square close packing. Remember, it is close packing in two dimension. In two dimension, the first type of arrangement that we are going to discuss is square close packing. The first row. This is one dimension which was arranged earlier. The second row is placed in contact with the first row. That is one above the other. It is placed like this, which is not efficient. From the arrangement itself, it's clear it is not an efficient type of packing. The spheres of the second row are exactly above the first row. The spheres of the rows show a horizontal as well as a vertical alignment. The arrangement looks good, but it is not an efficient type of packing. Here, each sphere is in contact with, you can see here, each sphere, the center, is in contact with 4 of its neighbors. And hence the coordination number of this type of square close packing is 4. There are 4 particles which is surrounding a particle. The center of these 4 spheres, as you can see there, the center of these 4 spheres are at the corners of a square. And hence this packing is called a square close packing in 2 dimensions. Second type of close packing in 2 dimension is hexagonal close packing, which is more efficient. The first row is arranged in this manner. Spheres in the second row are placed in the depression between the particles of the first row. So there is a space in the first row. There is a depression in the first row. And the second row is actually placed in the depressions of the first row. If the particles in the first row represent A type, the one being in the second row is different and can be called a B type. The first row is A type, the second row is placed in the depression is different, so it is the B type. The third row, when it is placed in the depressions, the third row aligns with the first row. It's similar to the first row, that is A row, while the fourth row aligns with the second row. So is that clear? So this type of arrangement, you can say the AB type. This type of arrangement is called AB type. This arrangement is AB type. Here, each sphere is in contact with 6 of its neighbors. You can see here, each one is in contact with 6 of its neighbors. and the coordination number is 6 here. The centers of these 6 spheres are at the corners of a regular hexagon. You can see here. And hence this packing is called two-dimensional hexagonal close packing. This type of packing gives triangular voids. You can find here the voids are the spaces or gaps after the filling has taken place. So gives triangular voids and is more efficient way of packing. So this from the diagram itself we can understand clearly that this is more efficient, this is more packed, less number of voids or gaps are there. That is why this is more efficient. We can find in the red portion the apex of the triangular voids point out opposite to each other in every adjacent row. You can see here the apex are opposite to each other. The red portion that is shown here are opposite to each other. Hexagonal close packing is more efficient of these two-dimensional close packing structures. So next what we are going to discuss is close packing in 3 dimension. That is, in solids, the constituent particles are close packed, leaving the minimum vacant space, which we have discussed earlier. So the next is in 3 dimension. We are going to arrange it 3-dimensionally. Packing of solid spheres in 3 dimensions is obtained by stacking 2-dimensional layers one above the other. 2 types of arrangements are possible here: square close packed and hexagonal close packed. This is very important. The main idea about close packing that you should know for doing problems is a 3-dimensional. So close packing in 3-dimensional is easy to understand, but you should understand before that what is the arrangement in 1 dimension and 2 dimension. The first, let us go to the square close packed layers in 3 dimension. The first layer, we have learned the first layer, the arrangement. Second layer is the spheres are placed one above the other. The third layer also, it is aligned one over the other. Fourth layer, again, it is aligned with the first, second, third, all are one above the other. In this arrangement, spheres of both the layers are perfectly aligned horizontally as well as vertically. So this type, all the layers are of the same type. So this can be, this simple cubic lattice formed here is a type of arrangement because all the layers are same here. And this is a simple cubic lattice. Its unit cell is a primitive unit cubic cell. This is how actually it is arranged. What we have learned earlier, as I had mentioned earlier, it was simply represented by points, but this is the actual arrangement of the solid particles. The particles are at the corners and hence it is called a simple unit cubic cell. This type of packing is not an efficient close packing that I have mentioned earlier. The second type, which is more efficient, the packing is more close packed. It is hexagonal close packed layers in 3 dimensions. So we are discussing about close packing in 3 dimensions. First one is over. The second one is hexagonal close packed layers in 3 dimensions. Placing second layer over the first layer. Consider a 2-dimensional hexagonal close packed layer. Here the layers are placed in the depressions of the first layer. As we had mentioned earlier, you'll be remembering that. Here, placing the second layer, the blue ball, the first is a green ball shown here. The second layer is colored blue and that blue is placed on the depressions of the first layer or spaces in the first layer. It's not placed one above the other. It is not aligned with the first layer. The spheres, as you can see here, the spheres of the second layer are placed in the depression of the first layer, and that is why we are saying this is more efficient type of packing. So the first layer and the second layer is different. So first layer we'll name it as A. The second layer we'll name it as B. We'll now refer to the bottom. It's given here, bottom, that is green one as A and the other bluish color as B. Here you can find there is a void. What is a void? A space or a gap formed after the close packing. So there are two types of gaps or voids. These gaps are actually called voids. So here you can see that the first layer is there, second layer is there, and that is a tetrahedral void shown here. What do you mean by tetrahedral void? That void is surrounded by four spheres. That is, the four spheres are at the corners of a regular tetrahedron, and hence that type of voids or gaps are called tetrahedral voids. Next is the octahedral voids. Here the red portion that you can see is the tetrahedral voids. There are also other type of voids called the octahedral voids. And what is the specialty of an octahedral void? That space, in that space you can find there, it is surrounded by 6 spheres, 3 at the bottom and 3 at the top. And hence the 6th one are at the corners of an octahedron. So let us see this. The two types of voids. The voids or gaps in close packing. 3-dimensional close packings of spheres have two kinds of voids. The 3 spheres are there. This is a trigonal void actually, the first layers. And the 4th sphere, that is the blue one, you're placing it above it. The 4th sphere is placed above it. And here, see, you can see here, the 4 spheres are the corners of a regular tetrahedron. Hence, that type of void is called the tetrahedral void. If the triangular void in a close-packed structure has a sphere directly over it, there results a void with 4 spheres around it. Such a void is called a tetrahedral void, since the 4 spheres surrounding it are arranged in the corner of a regular tetrahedron. Now, what is an octahedral void? You can find here there is a void in the center, which is surrounded by 6 spheres. There's a green portion here, the blue portion there. See the arrangement, the void space. The corners, it is at the corner. There are 6 spheres at the 6 corners of an octahedron. If a triangular void pointing up in one close-packed layer is covered by a triangular void pointing down in the adjacent layer, then a void surrounded by 6 spheres results. Such a void is called an octahedral void, since the 6 spheres surrounding it lie at the corners of a regular octahedron. The number of these two types of voids depends upon the number of close-packed spheres. So this part is very important to understand how many octahedral voids and how many tetrahedral voids are there for a packing, for a crystal system. So consider, let the number of close-packed spheres is n. N can be any number, like it can be 25, 30 or anything. If the number of spheres or number of particles is n, then after the hexagonal close packing is over, the number of octahedral voids generated would be n itself. It would be same as that of the number of spheres in it. But the number of tetrahedral voids generated, tetrahedral voids are smaller. So that would be 2 times the number of spheres. So this is the most important part for doing some problems. So let me repeat it. If there are n type of particles or n type of spheres, then after the close packing is over in hexagonal close packing, the number of octahedral voids would be equal to that of the close packed spheres, while the number of tetrahedral voids would be 2 times the number of close packed spheres. Close packing in 3 dimension, hexagonal close packed layer in 3 dimension. The second part we are continuing. The second type, placing the third layer over the second layer. Now we are placing the third layer over the second layer. There are 2 choices for the third layer of the sphere. That is, you can find here, one here. Third layer can be placed here or here. Here it is octahedral void. Here is the tetrahedral void. So you can place the third layer in two ways are there. Okay. See, the third layer is placed here. Third layer can be placed on the tetrahedral voids. Here, the purple colored balls are placed covering the tetrahedral void. That's one type of arrangement in hexagonal close packing type. So in this type of arrangement, you can find here the bottom layer is A, the second layer is different, but the third layer placed on the tetrahedral void is, in this case, the spheres of the third layer are exactly aligned with those of the first layer. Can you find that? The third layer, when it is placed on the tetrahedral void, it is the same type A, and that one is also A type, so it has to be A type. For this reason, we also label the third layer as A because the first and the third are the same. This structure has the form AB type. That is, when you are arranging in this manner, the third layer always will be aligned similar to that of the first layer. So here you can find here A, center is B is different and A is same. A type. The AB type stacking of close packed layers is called hexagonal close packing, or in short it is HCP, because the smallest lattice repeat is a primitive hexagonal unit cell covering tetrahedral voids. So here the coordination number. The coordination number of the atoms in this structure is 12. In this type of arrangement, when the third layer is covering the tetrahedral voids, the one in the center is surrounded by, you can find there 6 around it, 3 above becomes 6, 7, 8, 9 and 3 below, 9, 10, 11, 12. So the one in the center is surrounded by 12 atoms. So the coordinate is very important. The coordination number of the atoms in this type of structure is 12. They have 6 nearest neighbors in same close packed layers. 3 in the layer above, as I had mentioned earlier, 3 in the layer below, and 6 in that layer. The examples of HCP are magnesium, zinc, cadmium. Next, covering. The third layer can be placed in such a manner so that the octahedral voids, as mentioned above, can be covered. So here the arrangement is covering the octahedral voids. So the first layer is A, the second layer is B, the third layer is not aligned with the first layer, it is different. In this case, the spheres of the third layer cover the octahedral voids. The spheres of the third layer are not aligned with those of either the first or the second layer. For this reason, we label the third layer as C. So here it is A, B, C type. It's not this one. This arrangement is called, I see this is wrong here. It is A, B, C type. So there is a third layer is different here. When the fourth layer is placed, its spheres are aligned with those of the first layer. So this pattern of layers is A, B, C. Again, the fourth layer, when it is coming, it becomes the same. Will be having the same alignment as the first layer. So this is called A, B, C, A. Again, repeating it, A, B, C type of arrangement. Covering the octahedral voids, the unit cell. How is the unit cell? The first layer, the second layer, the third layer, and the fourth layer is the same here. The unit cell you can find here. What type of unit cell is this here? ABC type stacking of close packed layers is called the cubic close packing type. So when the fourth layer is similar, the other one was HCP, hexagonal close packing. This type of arrangement is called the cubic close packing. In short, it is called the CCP, or it is a face-centered cubic type of packing because the smallest lattice repeat is a face-centered unit. The coordination number of this type. The coordination number of atoms in this structure is 12. They have 6 nearest neighbors in the same close packed layer, 3 in the layer above, 3 in the layer below. Examples are aluminium, nickel, copper, silver, platinum, etc.